I'm your guide for today's journey through deep time, a science communicator in field and museum. The story we're entering is the hardest one I know, the day life almost died. Roll the clock back to 252 million years ago, the very end of the Permian. Earth wore a single giant continent called Pangaea, ringed by a world ocean. Belts of desert spread like rust across its interior. Dry and harsh, forests clung to coasts and uplands, while reefs rimmed clear continental shelves. River systems braided across vast plains, feeding wetlands and fertile valleys. Reptile kin with saber teeth hunted, while burrowing herbivores grazed scrubby plants with beaks. The planet was not a quiet place, but it was full, layered, and inventive. Then something deep in the engine room of Earth changed without mercy. Far to the north, in what is now Siberia, the crust cracked and kept cracking. Fountains of lava poured out in pulses lasting thousands to hundreds of thousands of years. Imagine flood basalts laid like blankets of black stone, stacked one atop another. These flows formed a province large enough to cover a corner of a continent. They were thick enough to hide a skyscraper inside a single frozen sheet. This was not the sudden bite of a single asteroid or comet. It was a furnace turned on an Earth's basement with every knob stuck at maximum. To understand the end of the Permian, you begin in landscapes like this. But you also listen to quieter rocks that preserve the consequences far away. In my field notebook, I've sketched the same pattern from different corners of the world. Limestones full of shelly life give way to darker, lifeless shales in the record. Burrowed sandy seafloors turn to fine muds that speak of still, stagnant water. Fossil lists that once ran long down a page dwindle to a few stubborn names. One layer holds rain-etched soils, another charcoals baked by ancient firestorms. Above them, chemical signatures tell of air and sea shifting at dangerous speed. These are not rumors, but recurring chords of a planet's song when it runs a fever. I stand today at a cliff face that tells this story in stone. Imagine a limestone wall the color of old paper, stacked like pages in a book. In places from China to Iran to the western United States, the same change appears. We trace a boundary you could hide behind a fingernail, thin but world-shaking. Above it, the rock turns darker and muddier, fossils thinning to almost nothing. That wafer of time is a hinge in Earth's biography, the Permian Triassic boundary. Passing it in the rocks is holding hands with a crisis that rewrote life's future. I bring students here and ask them to run a fingertip along that narrow line. Picture not one bad day, but a long emergency with echoes across millennia. When I learned this in grad school, I doubted a disaster could be so swift geologically. But the rocks keep repeating the same refrain across continents and seas. We find a sharp plunge in carbon isotopes, a fingerprint of a carbon-heavy atmosphere. We find spikes of ash and mercury, the ghost of feverish volcanoes still lingering. We find soils etched by acid rain, charcoal from colossal wildfires in the strata. In oceans, black shales mark the moments when deep water stopped breathing. All clues point toward the Siberian Traps, where heat and chemistry conspired. Picture them not as one mountain belching, but as a province sprawling for millions of square kilometers. Eruptions came in pulses, stacking basalt flows kilometers thick over time. Between those fiery blankets, hot magma wormed into coal beds and salt deposits. It cooked organic-rich sediments like a furnace, driving more than lava into the air. Carbon dioxide, methane, sulfur, chlorine, fluorine, and aerosols rode the global winds. Some gases warmed the climate while others shaded it temporarily from the sun. Some made rains more acidic, some gnawed at the planet's ozone shield. The point is not one gas did everything, but overlapping stresses hit at once. Ecosystems face changes faster than their capacity to recover or adapt. This became the worst mass extinction in the last half-billion years of life. The cause was not one villain, but a chain reaction of environmental pressures. Volcanoes loaded the sky with greenhouse gases, driving global temperatures up. On a supercontinent, heat built inland where oceans could not carry it away. Warmer air held more water, making storms swing wider and droughts grow deeper. On land, soils eroded under erratic rains, sending nutrients into the sea. The influx fueled algal blooms that died and rotted, stripping oxygen from water. Breathless seas forced animals either to flee or to suffocate in place. Acidified waters made building shells harder, hitting corals and plankton at the base. It was never one blow, but a pileup of stresses without pause. I think about those who pieced this together over decades of research. Field geologists traced boundary beds across mountains in heat and cold. Paleontologists logged the last appearances of trilobites and the stutter of ammonoids. They recorded the faint hope of tiny survivor lineages clinging on. Geochemists sampled at dawn to keep flasks free of modern carbon contamination. We argue details, cheer new clues, and chase the truth of how worlds fail. In this work there is humility. Life did not quit, it staggered and rewove itself. That resilience, too, is written in these rocks for those who read them. Stay close. In the next breath we'll follow the killing chain into the sea. Let's follow the cascade. First came the fever. When volcanoes push vast volumes of carbon into the sky, the planet traps more heat. The oceans absorb much of that carbon, turning a little more acidic over time. Shell builders struggle first because their chemistry balances on a knife edge. Corals, some plankton, and many shellfish find the cost of making skeletons rising. This happens just as food webs are beginning to wobble under strain. Warming also slows the churning of surface and deep waters across the seas. Oxygen that waves froth into the ocean no longer reaches the depths as efficiently. In that quieted ocean, animals that need steady breath run out of room to live. Then comes a second blow, the stench of rotten egg chemistry. In many basins we find evidence that waters turned breathless and poisonous. They became rich in hydrogen sulfide, the same gas from hot springs that kills fish in minutes. When that kind of water wells up toward the light, it remakes the sea into a hostile factory. The record captures this in black shales and sulfur minerals formed without oxygen. Fossil communities that were once bustling suddenly look like ghost towns. On land, the stress was no kinder to life. Forests that anchored soils and shaded rivers suffered debacks and firestorms. Their loss sent silt and nutrients rushing into lakes and seas in destructive floods. That feedback fed the ocean's oxygen crash and spread the damage further. In the tropics, heat pushed the limits of what warm-blooded bodies can shed. The livable zones for large, active animals shrank until few could survive there. We see this not only in climate models, but in the fossil record itself. In South Africa's Karoo Basin, the last Permian predators thin out and vanish. A handful of hardy herbivores persist in open, stress habitats across the plains. The severity still makes people blink even after years of study. By the end of the crisis, 9 of every 10 marine species were gone forever. On land, 2/3 to 3/4 of vertebrate species disappeared. Whole styles of life ended in the space of geological heartbeats. Trilobites, survivors of every prior catastrophe since the Cambrian, ended here. Reef systems built by rugose and tabulate corals collapsed entirely. They would not truly return for millions of years afterward. Conifers, seed ferns, and scrappy pioneer plants took over raw, eroded landscapes. How fast did it happen? Fast enough to outpace adaptation? Yet not in a single afternoon. Some boundaries look knife-sharp, but zooming in reveals a pulsing rhythm, bursts of eruption, intervals of warming, and episodes of choking seas. These pulses stretched over tens to hundreds of thousands of years. That rhythm matters because long enough pauses can let ecosystems heal. Here, the pauses were too short. Recovery steps were kicked away by the next wave. Think of a runner trying to catch breath only to be shoved under again. I've met people who carry this story in their hands every day. In Nevada, a team kneels at sunrise to pick tiny conidant teeth from sediment. They look like grains of rice but hold a diary of ancient seawater chemistry. In South China, a researcher samples a creek where anoxic springs burp deep gases. They use today's odd corners to test yesterday's extinction hypotheses. In a Cape Town lab, Anna cleans a Lystrosaurus skull with a brush as soft as an eyelash. She holds the face of a survivor that marched into the Triassic when so many did not. Each of these people is part of a relay, and the baton they pass is evidence. Still, one more twist completes the trap that held life down. As carbon climbed and continents baked, weathering on land sped up, rivers carried dissolved metals into the sea, altering life's chemistry again. Some metals fed plankton blooms, others poisoned them outright. Volcanic aerosols stripped ozone, letting more ultraviolet light strike the surface. That stress still lingers as scars in the fossil pollen we study. Even the sky would have told the story to eyes that could see it. Hazy, ruddy sunsets marked ash veils after eruption pulses. Lightning crawled across dry storms over continents baked to dust, no single blow enough to end a biosphere. It is the combination, the overlap, and the lack of time to recover that does the work. In coal seams, we find a startling lull called the coal gap. Thick peat-forming forests vanish in many regions for millions of years. This is not just a missing page in the record, it is a collapse of wetland ecosystems. With them went habitats for insects, amphibians, and small vertebrates breeding in shaded waters. In shallow seas, we see the rise of so-called disaster taxa. Hardy bivalves and brachiopods spread where complex communities once stood. They tolerated murky, low-oxygen conditions that others could not endure. In many rock sections, we detect spikes of volcanic mercury, settled far from its source. We read swings in carbon isotopes that map the breadth of the global carbon cycle. None of these signals alone would be enough to convince us. Together, they braid into one sobering story. They trace a planet overwhelmed and a biosphere brought to its knees. Morning light on a rock face shows that endings are also thresholds. Above the boundary bed, the Triassic begins not with fanfare but with persistence. In muddy river margins you find burrows from little animals that kept moving when giants could not. In the first millions of years, fern spikes mark bursts of regrowth after fires. Conifers claim uplands, and hardy lycopsids stitch wetlands where they can. In the oceans, survivor lineages take the stage and begin to rebuild. Ammonoids rebound with dizzying turnover in the early Triassic seas. New coral groups tentatively build frameworks in scattered shallow waters. Simple communities assemble before true complexity returns to the oceans. Ecosystems are not light switches, they are tapestries rewoven strand by strand. Recovery took time measured not in generations, but in millions of years. From those years rose innovations that shaped the rest of the Mesozoic. On land, the cast also shifts to a new set of survivors and pioneers. In South Africa's Karoo, herds of Lystrosaurus roam floodplains like tough, squat lawn mowers. Their beaks scuff dusty ground that used to be shaded forest. Archosaur relatives diversify, setting the stage for dinosaurs and pterosaurs later. Cynodonts, our own mammal-line cousins, refine jaws and teeth for future success. I think about that while hiking between outcrops with a teacher named Tom. He draws animals to explain science to his high school students each year. Tom once thought of mass extinction as a comet strike and a fade to black. Now he sketches timelines that breathe with pulses of stress and recovery. He draws experiments in survival and the uneven rise of novelty that follows. On a ledge, he opens a lunchbox and shows me a pencil stub for sketching ammonoids. Later, we visit a museum prep lab where Anna works on a Triassic amphibian. Her hands move in patient arcs as she cleans the matrix from its bones. She says she likes preparing survivors because every bone feels like a vote for persistence. Stories change the people who tell them, just as science changes those who do it. Tom starts bringing his students to the outcrop each spring without fail. Anna begins a weekend program for kids who want to learn the fossil trade. I start building this episode with hope that accuracy can share space with wonder. What broke the back of Permian ecosystems was not one single stress. It was the speed, scale, and stacking of multiple stresses together. Today we are changing the atmosphere and warming oceans at alarming rates. That does not mean we are destined to replay the End-Permian catastrophe. It does mean that the rate of change matters for survival and recovery. Coral bleaching events show how quickly a threshold can be crossed. Shifts in ocean oxygen and the spread of marine heat waves are clear signals. Changes in wildfire seasons echo patterns we see preserved in the rocks. The physics of energy, water, and carbon has not changed in deep time. So, what is the lesson from this ancient and sobering story? First, humility. A planet can be pushed until the rules of life change entirely. Second, agency. We are the first species to see a disaster coming in time to steer away. The Siberian Traps taught by accident. The samples and models they inspired are our tuition. Every ton of carbon not sent skyward widens the pause between devastating blows. Time is the currency of adaptation, for us and for all living systems. When I send students into the field, I ask them to find resilience in the record. They point to tiny clam trails above a dark shale that tell of life's return, or to a bank of cross-bedded sand that means rivers ran again through the land. We talk about how complexity is a savings account for ecosystems. The more ways energy can flow through a community, the more shocks it can absorb. We walk back along the cliff in golden light as the day ends. We trace the thin layer that marks a bad day stretched into geologic time. I tell them the biosphere is not fragile glass, but it needs breathing space between hits. Diversity that shares the load is as important as the space between crises. Because the end of the Permian was not the end of life's imagination. We stand now at the far edge of that arc of recovery and innovation. If there's a message from this cliff, it is that knowledge is a lever for change. We cannot move mountains with a single hand, but we can choose the fulcrum wisely. We can ask more hands to join in classrooms, city councils, and design studios. In shipyards, people are already planting shorelines and lighting efficient beacons at sea. We take readings, we set baselines, and we share them widely for action. Data is how a species as messy as ours learns to act together effectively. Before we leave, Tom sketches one more ammonoid in a fresh notebook page. He hands the spiral to a kid who has been listening quietly from the back. The spiral is open, always turning outward into the next possibility. Our place in this story is to keep the pauses long and the options many. We must keep the living world full of ways to pass energy along safely. The rocks do not demand perfection from us. They ask for courage and steadiness. They ask for attention to the signals and to the connections that sustain life. Then I look up at a sky the color of slate and feel something clear and stubborn. Against long odds, life rebuilt once before. Our job is to make rebuilding easier now. We still have the window wide open, but it will not stay open forever. Thank you for walking this ridge with me, for staying curious, and for listening. Carry a piece of this timeline into the choices you make when you go home. We listen and we act, because the story is still being written now.